Okay, we're continuing with Chapter 2 in the algebra textbook. In this video, we're going to go through the third section, which is on functions and relations. Okay, so as we've been talking about, one of the main purposes of what we're doing in this chapter is we want to learn how to analyze relationships between variables, two or more variables. And most of the time, what this is referring to is relationships between two or more variables in an equation or an inequality. Okay, now, so if we start with the simplest case of an equation in two variables, okay, then if you think about it, the absolute bare bones fundamentals of how we're analyzing that relationship between the two variables is with a set of ordered pairs. So a set of ordered pairs, so there's two variables. Let's say, okay, you got x1, y1. There's one ordered pair. x2, y2. There's another ordered pair. And you just keep going and however many ordered pairs there are. Okay, that's the fundamentals of what we're doing. If we've got an equation in x and y, we can input an x and then get an equation in one variable and solve for y, and we get an ordered pair. We can input another x and solve for another y, get another ordered pair. We can input a y and solve for x and get however many ordered pairs we want. And in the case of an equation, there's an infinite number of ordered pairs. Okay, but it's not like you always have to be dealing with an equation or an inequality to be analyzing the relationship between two variables, two or more variables. It could be any situation. Maybe it is you have some situation where you do only have like 5 data points and that's it. Well, now instead of having a set of infinite ordered pairs like what an equation would be, now you've got a set of these 5 ordered pairs. Okay? But that's fine. I mean, you can still, with these 5 ordered pairs, you can still analyze the relationship between these two variables. And so that's why this is what we call a relation. Any set of ordered pairs pertaining to some system or situation, you call that a relation. And note, I'm saying set of ordered pairs. We're really referring to a group of these ordered pairs. Technically, we could just have one that would still be valid technically, but in general, we're referring to a group, either a finite group of like 5 like this, or an infinite group like an equation would be. Okay, that's what's called a relation. Now, so we're keeping this simple at the moment. We're just thinking about a relation between two variables, but a relation is when you're analyzing relationships between two or more variables. So in that sense, we could have, if we were analyzing the relationship between 3 variables, either in a 3-variable equation or inequality, or just some system that we're just writing down some data points and we get like 10 data points. Okay, so in that case, you would represent that as these ordered triples. Okay, etc. And when it comes to these relations between 2 or 3 variables, we actually can graph that and visualize it. If it's an equation, we'll get a smooth curve because there's an infinite number of points. If it's not an equation, just like a finite number of points, then we'll just have these points plotted throughout 2D or 3D space. But again, you can still go past, as we've talked about, you can have a relation between 5 variables, 6 variables. And maybe you can't really graph that, but still, that's still fine. You could have a relation between 5 variables would be this group of x1, y1, z1, p1, w1. This group of these 5 points, these whatever you call that, these quintuples, I guess. Okay. So here they give some examples of some real-life circumstances where you're analyzing these relationships between variables. Variables or quantities they're subject to change. That's the whole idea. Any of these variable quantities that you're analyzing the relationships between, they're subject to change. So they could be different values depending on the circumstance. So, for example, the cost of mailing a package is related to the weight of a package. So you could take a bunch of data points. You could say, okay, we just received a package. That's this package's weight, and this was the cost of mailing it. Then another package comes in. It weighs a different weight, different cost. And you get however many data points. And that's that group of data points, that's a relation. And then if you, I guess, made an equation out of this, then it turns into like an infinite number of points. That's still a relation between two variables. The minimum braking distance of a car depends on the speed of the car. If it didn't, if for some reason the speed of the car didn't matter, it was always the same braking distance, then the speed of the car wouldn't be a variable. But we know that it is. The braking distance and the speed of the car, those are, in that system, those are different. Those quantities are going to be different depending on the circumstance. They're variable. In the kayaking example we talked about, the time it takes to kayak all the way across like a swamp basin or something, I forget what it was. Well, if the current we assumed was constant for all circumstances, maybe it is. Maybe the current in general is always the same, in the same direction for some reason, in general. So that would be a constant. So if you're trying to figure out, okay, how much time is it going to take me depending on how hard I paddle, well, I don't have to think about the current changing. As long as in general it doesn't change significantly. Okay, so, but they're focusing here on ordered pairs to keep it simple, but just let's keep in mind that this could be two or more variables to have a relation. Okay, but it says in mathematics we express the relationship between two values as a set of ordered pairs. A set of these ordered pairs or ordered triples, ordered 10 values, whatever. A set. It's a group. Okay, you call that a relation. And again, notice how an equation, fundamentally, an equation is a relation. It's an infinite number of these ordered pairs or however many variables. So it's a set of ordered pairs, x, y, is called a relation in x and y. This is a relation in w and c. This is a relation in x, y, and z. Like this is a relation in x, y, and z. This is a relation in w and c. This is a set of 3 ordered pairs. This is a set of 3 ordered triples. Okay. The set of x values in the ordered pairs is called the domain of the relation. The set of y values in the ordered pairs is called the range of the relation. So what they're talking about here, if we stick with ordered pairs, the idea is you're kind of looking at this like it's a machine in a sense. And you're only like what the domain is what values are you allowed to input, in the sense that when you input those values, you're going to get an output. So if we had, let's see, if we had a set of these ordered pairs, okay, here's this relation here, this group of 5 ordered pairs. The domain is, if you have to input either 2, 5, minus 7, 12, or minus 5 in order to get some output. So that's what the domain is. The domain is 2, 5, minus 7, 12, minus 5. If you input something else other than that, it's going to say there's no solution, no answer. So the set of valid inputs, I don't want to say valid because that implies that if we inputted 11, that's invalid. I mean, no, that's a number, right? But it's more of so it's really, the domain is this. It's what is the set of all inputs that will result in an output. Okay, that's the domain. Now the range is the set of all of the outputs you could possibly get. So if no matter what you input, what is the only possible outputs you could possibly get, no matter what you input? That's the range of a relation. Now, okay, but what about if you've got more than 2 variables? What's the domain and range in that case? Well, that's just going to depend on the specific circumstance. So it might be the case that if you've got this set of triples, ordered triples here, well, in general, the way we typically look at an equation in 3 variables, or even if this wasn't an equation, is you input an x and y, and then what's going to get output is z. So in that case, the domain would be the set of all XY pairs that are going to result in an output Z. But it just depends. You have to look at you would kind of define this in the sense that, so like the cost of mailing a package is related to the weight of the package. Well, okay, in that sense, it's like the input is the weight of the package, right? And then the output is the cost to mail the package. But maybe there's other factors that affect the cost other than just the weight, the size, right? So the inputs would be, okay, the size, like the size of the package and combined with the weight of the package, those are inputs. And then the output is the weight. But you could also you could label outputs with, there's more than one output in the sense of, I mean, whatever, it's how you, the perspective you look at it from. So, okay, like the inputs are the weight of the package, the size of the package, whatever. And outputs you could look at as cost and what's something else that's kind of like an output of that? Shipping time, maybe. It would all be up to you to decide what is, do you view that as more of, that's an output of inputs. Shipping time and the shipping cost those are more of outputs. That's a result of the inputting factors, right? So in that case, you would have this set of these points with 4 dimensions here. The inputs would be all acceptable, all X, Y pairs that result in an output, and that would be the domain. All X, Y pairs that result in an output, and the range would be all of the Z, W pairs that you could possibly get. So let's take a look at this example here. It says table 2.1 shows the score Y that a student earned on an algebra test based on the number of hours spent studying 1 week prior to the test. So the number of hours spent studying 1 week prior to the test, the student studied for this many hours 1 week prior to the test, and here's the resulting test scores. So this is a relation, right? This is a relation. There's no equation here, but this is still a relation. It's a set of these 5 ordered pairs. So now it says, write the set of ordered pairs that defines the relation. Well, so we're just, it's the set. Remember, we write a set with these, we open a set with these curly brackets, and now let's just write all of the ordered pairs. Okay, so there you go. Now, this is like, technically from a mathematical perspective, this is how we write a set of ordered pairs. If we can actually write them, there's a finite number we can write out. But from an informal standpoint, to me, this is you can just write it like this in a table. Here's the set of ordered pairs, right? So, okay, but now what's the domain of this set of ordered pairs? What's the domain? Well, the domain is the set of numbers 8, 3, 11, 5, 8. And actually, well, no, but we don't put duplicates. So I just leave off this 8 here. There's no reason to put duplicates. So this is the set of all inputs that you can input into this relation, and you're going to get an output. If you input anything else, you're not going to get an output. Okay, now what's the range of this set of ordered pairs here? Well, we can see it's 92, 58, 98, 72, 86. That's the set of all values you could possibly get out of this relation. Okay, now, the next thing we want to think about is that there's specific types of relations that we're going to want to put into their own special category because they're really important. They're something that we use a lot. It's a type of relation that we frequently use. Okay, so it says here, the data in table 2.1 with the test scores show 2 different test scores for 8 hours of study. That is, for x is equal to 8, there are 2 different y values. In many applications, we prefer to work with relations that assign one and only one y value for a given value of x. such a relation is called a function. So yeah, if you look here, if we come back here, what they're saying is that if one thing we could notice about this for this relation is that we have the same input here, x is equal to 8, but the outputs are different. With 8, x is equal to 8 here, you got the test score is 92. With x is equal to, with 8 hours of study here, in the week prior, the test score was an 86. Well, so what? What's the big deal? That makes sense. For 2 different tests, you studied for 8 hours on both tests, but the test scores were different. So what? Well, okay. Think about circumstances that you commonly deal with in real life. If you went to an ATM machine and the ATM machine was coded in such a way that, so you're selecting all kinds of stuff, and then you select something, and now the final result is the ATM machine, the code tells the ATM machine the final function to perform. It says output $20 and $80. It says to output both $20 and $80. Well, that's a problem. The machine's going to say, well, well, which one? I'm not saying output 20 plus $80. I'm saying it's like you selected that you wanted $20 out, and the machine tells it to do like 2 things at the same time. Like you need one output. It would be like for the cost and weight of the package relation, assuming there's no other variables that are a factor. Let's just assume that. Well, you can't have the same weight package. You can't have a 5-pound package in one circumstance, resulting in it costs $5 to ship. In another circumstance, it costs $7 to ship, assuming there's no other variables involved. Then no, I mean, then what does this mean? You need one answer. Okay, so there's a lot of applications. If you think about the different types of real-life applications that involve relations between variables, a lot of them have this kind of requirement where you can't have different outputs being associated with the same input. It just doesn't make sense. There's a lot of applications that are like this. Now, it's not every relation. We just saw an example of a relation that's not a function. But again, a lot of relations are going to be functions. Okay, and so if we look at the definition of a function, it says, given a relation in x and y, we say that y is a function of x if for each value of x in the domain, there's exactly one value of y in the range. Okay. Now, the first thing to note is that here they just gave a description of a function in 2 variables, so we want to think about how this extends to more than 2 variables. But we'll come back to that. Now, but what you might notice about this is that it does make sense to have 2 separate inputs correspond to the same output. So maybe let's think about a slot machine. You can't have the machine computer, if you land on a certain configuration, it can't say give $50, but then also it says give $100. I'm not trying to imply that you would give $150. I'm saying it's like it tells it to do 2 separate things at the same time. It would break the machine. Okay, it has to, okay, here you got the, whatever it is, the cherries and this and that. That means give the player $50. You have to give one output for any input. But it does make sense that there could be 2 separate configurations that you get with the slot machine to where both of those, the result is the prize is $50. That makes sense. So it's still a function if you have separate inputs corresponding to the same output. It's just not a function if you've got the same input mapping to 2 or more outputs. Okay, but again, note that it's not like there's no such thing as a relation that to where you have one input mapping to multiple outputs. No, we just saw an example of a relation like that. Right now we're talking about a special kind of a relation that we call a function. Okay, but what about multiple variables? How does this definition of a function, on the previous page, we talked about relations involving multiple inputs or multiple outputs, how does a function come into play here? So in this case, we had, I think we were talking about, what was it? The volume and the weight of the package, and then output is the cost to ship and the time to ship. Well, that's multiple outputs, so that's not a function. No. You would still label this as a function as long as if you have an XY pair, for every XY pair input, there's one and only one ZW pair output. In that sense, you're looking at these outputs as vectors in 2 dimensions. So for this would be a vector input, a two-dimensional vector input, you get one and only one two-dimensional vector output. That's the idea. You couldn't have, if you input a certain weight package with a certain, it takes up a certain amount of space, you couldn't have the output telling you, okay, this is going to cost $50 to ship in 3 days, and it's also going to cost $80 to ship, and it's going to take 5 days. Well, which one is it? You see? Okay, let's look at this example here. Determine if the relation defines y as a function of x. So part A, is this set of ordered pairs a function? Is this relation here a function? And we're going to assume that the first parameter is the inputs x, and the second parameter is the outputs y. So the first thing we want to look for is, are there multiple of the same input, either duplicates or maybe there's 3 of the same input, whatever. If there's no input anywhere that's repeated more than once, then it's a function. Because in that case, how could you have the same input mapping to separate outputs? You have to have multiple of the same input. Okay, so let's see. 3, 2, -4, -1. Not yet. We haven't repeated any inputs yet. 3. Okay, so we've repeated the input 3. So now all we need to do is see, are the outputs that correspond to these 2 inputs of 3 different? 1, -4, yes, they are. So no, it's not a function. You've got the same input mapping to a different output. Okay, here, let's see. Are any inputs ever repeated? -1, 2, 3, -4? No. So we don't even need to check the outputs. You never have the same input anywhere. So that is a function. Okay, so it says a relation that is not a function has at least one domain element, x, paired with more than one range element, y. For example, the ordered pairs 3, 1 and 3, -4 do not make up a function. On a graph, these 2 pairs are aligned vertically. A vertical line drawn through one point also intersects the other point. This observation leads to the vertical line test. So we can think about how we could test to see if a relation is a function by looking at its graph. And if we're focusing on a two-dimensional relation, we could test to see if a two-dimensional relation is a function by analyzing its graph, even if it's just a set of ordered pairs, not an equation with a smooth connected curve. You can still graph a set of ordered pairs as a set of points. We can test that graph using what's called the vertical line test. And what they're saying is that if you can draw any vertical line anywhere on the graph of a relation, and just one vertical line passes through more than one point, then it's not a function. And that makes sense because the whole idea is that if you're drawing a vertical line, then that line is fixed on an x value. A vertical line on a two-dimensional graph has a constant. With the input being the convention is the input is going to be the horizontal axis. So if you draw a vertical line, then the input is constant, all on that vertical line. So if that vertical line intersects the graph at more than one point, well, that's more than one input corresponding to or more than one output corresponding to the same input, which means it's not a function. You see, and so they test the relation, the simple relation 3, 1 and 3, -4. There's its graph, those 2 points. They draw a vertical line, and at this, you could draw a vertical line anywhere you want, and it passes through more than one point. It's not a function. Okay, so the vertical line test Consider a relation defined by a set of points x, y, graphed on a rectangular coordinate system. The graph defines y as a function of x if no vertical line intersects the graph in no more than one point. So we're in a rectangular coordinate system, okay, and the relation is this set of points x, y, where y is a function of x. So the output is y on the vertical and the input is x on the horizontal. Then if no vertical line anywhere in the Cartesian plane intersects the graph at more than one point, then y is a function of x. You have a function. Okay, so let's see. Let's look at this example. The graphs of three relations are shown in blue. In each case, determine if the relation defines y as a function of x. So here we can see we've got these equations, these continuous curves here, these equations. So you can see that you can draw a vertical line anywhere in the plane here, and it's never going to intersect the graph at more than one point. That's a function. Here, you can't do that. Look, it intersects, the vertical line intersects the graph at 2 points. That's not a function. Here, it looks like, well, maybe you could do this. That intersects the graph at 2 points. Well, no, the graph isn't defined here. So no matter where you draw a vertical line, it's going to intersect the graph at just 1 point. That's a function. Okay, so it says a relation can also be defined by a figure showing a mapping between x and y, or by an equation in x and y. So let's take a look at what they mean by this first form here, a relation being a mapping between x and y. Okay, so they're saying that this is one way you can represent a relation. Here they've got this region of the x values are the inputs, and then each input is mapped to this region of the outputs, and it's mapped to a specific output with an arrow. And you could think about how you could try and extend this type of form here of representing a relation graphically to multiple variables, multiple inputs or multiple outputs. Okay, but is this a function? Well, first of all, just remember, if you're asking if a relation is a function, you have to be clear on what exactly are the inputs and what exactly are the outputs. Because it could be the case here, it could be the case that y isn't a function of x, but x might be a function of y. So you have to be clear on what exactly are you asking is a function. Here the question is y a function of x? So is y a function of x? That means that since x are the inputs, each input can only map to, you can't have the same input mapping to multiple outputs. So no, that's not the case here. Yeah, you have 1 and 3 mapped to the same output, but that's fine. You couldn't have one mapping to, you couldn't have two arrows going from the same input to different outputs, and that's not the case. So this relation is a function, okay? But as we've talked about, you can also, another form of a relation is an equation or an inequality. Y squared is equal to x. This is a set of ordered pairs. You can pick an x, solve for y, pick another x, solve for another y, pick a y, solve for x, and this is an infinite number of ordered pairs, which is that's a set of ordered pairs. That's a relation. And the same idea here. This is a relation in x and y. This is a relation in x and y. Okay, is this a function? Well, again, we need to be clear what kind of, so yeah, if we went in the other direction, if we said is just to come back here, if we said is x a function of y? Well, no, it's not, right? You have, if in that case, y is the input, and that's mapping to two separate outputs. So no, so we need to be clear if we're asking is this a function, what are we talking about? What's the specifics of the function? Well, again, is y a function of x? Well, okay, in that case, x is the input, so you've got like 4 for x, let's say. So okay, y squared is equal to 4. So we could solve this using the square root property. So you get y is equal to plus or minus 2. So that's one input, 2 separate outputs. No, that's not a function. And in this case, we're actually able to, since it's 2 variables, we can graph this in a Cartesian plane and do the vertical line test in a Cartesian plane. Note that. We haven't talked about the idea of how we would do a test for a function in another type of coordinate system. So, okay, here's the graph of y squared is equal to x, and it does not pass the vertical line test. Okay, what about this equation here? Well, we can see that's the equation of a circle centered at 2, -1 with radius 3. Well, just thinking about what the graph of a circle looks like, then we can intuitively think about how this is not going to be a function. You could draw a vertical line through 2, and it's going to pass through 2 points of a circle. Okay, but we can take a look at the equation and see that if we picked an x, let's say x is equal to 2. Okay, we're going to be left with what? Y plus 1 squared is equal to 9. Square root property. Y plus 1 is equal to plus or minus 3. Y is equal to -1 plus or minus 3. It's 2 points corresponding to one input, so no. Okay, so now function notation. Function notation. All right, so again, because functions are used so frequently, if you really think about it, you're going to notice if you really take a look at every time you're doing an algebraic model, if you're working in algebra, calculus, you're always really needing to use a function a lot of the time. If you really stop and think about it, it wouldn't make sense to, if you're trying to model for some word problem you're working on or something you're trying to model, it wouldn't make sense for there to be more than one output corresponding to the same input. So because this is so frequently used, and because it is kind of like, it's like a machine. It's like you're giving one or more inputs, you're putting one or more inputs into the machine, and it's spitting out an output for you. It's like a tool. A useful way to think about it is like you might be working at a business or something, or an engineering firm, and you've got these different algorithms saved on your computer, saved in with MATLAB codes. You have these MATLAB functions you could make. You put a bunch of inputs in and it gives you an output. Or you can have just other algorithms saved in your computer. It's like a tool shed, and you can pull out these different functions to use. Because of this, what you can do is you can use what's called function notation. Okay, so it says a function may be defined by an equation with 2 or more variables. But here we're just focusing on 2 variables. Yeah, any equation could potentially be a function if it passes the vertical line test. For example, the equation y is equal to x minus 2 defines y as a function of x. This is because for any real number x, the value of y is the unique number that is 2 less than x. Yeah, so in general, the idea is if you're trying to look at an equation and tell if it's a function or not, the easiest way to tell is if it either the way you're looking at it, or you can put it into a form where you've got one variable on one side by itself, and then on the other side is just one or more other variables. So maybe there's you could have some expression of x, z, whatever, but there's no y's over here. You have this one variable by itself and then over here is one or more other variables, but the y variable is not over here. And in addition to that, there's no like pluses or minuses anywhere. Like with the quadratic formula, you have a plus or minus. If there's no pluses or minuses anywhere, then it's a function. Because think about it. Think about the different types of expressions we work with. Even the radical. The whole purpose of the radicals is that it's going to give you one output. It's only when you add the radical to the equation manually that you have to think about the multiple outputs. No, if you just have an expression that you were given with the radical, that's one output. All of the operations that we work with, the exponents, etc., everything, it's one output. One output. So any expression here, as long as there's no y in it, it can have however many variables you want. If the y is by itself over here, it's going to be a function. Okay, and so when you have that, when you have a variable by itself, an equation that's a function, so you have this variable by itself on one side and all these other variables on the other side, you can write the function variable in what's called function notation. So you have y is equal to x minus 2. What you can do is you can change this to f of x is equal to x minus 2. if you had z is equal to x squared minus y squared plus 2y plus 3, you could write this as f of x y is equal to, and just write that same expression. And you call this is, you say f of x is equal to x minus 2, or f of x y is equal to x squared minus y squared plus 2y plus 3. And you'll see, like, if you make MATLAB functions, you can actually name your function whatever you want. You could, instead of just an f, you can name it whatever you want. Okay, and then even if you're going to make a graph, if it's just two variables, then you could do like this. But you can only do this if the output variable, the dependent variable, is a function. This would make no sense. To have a circle and then you're calling this f of x. No. Okay, and so with that, we can think about, so if we have the function g of x is equal to 2x plus 1, then what is g of minus 2? Well, you just plug in minus 2 for x. Okay, and now you might be thinking, well, man, why are we doing this? This seems kind of pointless. No, it can be very useful function notation can be very useful. And I think this will make more sense of why it can be useful when we get to the last section of this chapter. So just stick with this. Okay, so you can evaluate g of minus 1, g of 0, g of 1, g of 2. You can name this function whatever you want. You could give it a specific name. That's a lot more useful than just saying, like, having this be just y. It's a function name, right? And you're evaluating this function, whatever you name it, at different inputs. So we're going to work a bunch of problems where we evaluate functions in the next video. Let's see. So yeah, you can evaluate functions not just with numbers, but with anything. So 3x squared, f of x is equal to 3x squared plus 2x. What is f of a? Well, that's just 3a squared plus 2a. What is f of x plus h? Well, you just replace x with x plus h. And they expand this out and simplify, and there's f of x plus h. What would be the x and y intercepts of a function? Well, we already have learned how to find the x and y or any variable intercept for any variable in an equation in however many dimensions. So it was a simple idea. If we're assuming that we're plotting the equation in a Cartesian system, so here's a 2D Cartesian plane. You've got a 3D Cartesian coordinate system. But you can abstractly think about having a Cartesian system in any number of variables, even though we can't actually visualize past 3D. Then assuming we're in a Cartesian system where the graph of an equation intercepts any one of the axes, is just going to be where all of the other variables are equal to 0. So if we're going to be on the x-axis, so intercepting the x-axis, then y, no matter where we are on the x-axis, y has to be equal to 0. And it's the same idea here. If we're going to be intercepting the y-axis anywhere, then both x and z have to be equal to 0. And so you can extend this to an equation with any number of variables. If you want to find where the graph of that equation intercepts any one of those axes, then just set all the other variables equal to 0 and solve for that variable. Okay, and so, but now thinking about what the x and y intercepts of a function would be, well, a function is just a certain type of equation that we just call a function, and we're allowed to replace the kind of lone variable that we call the output variable with function notation. Okay, and so if we think about from the perspective of this function notation, what the x and y or any kind of intercept of a function would be, well then, okay, graphically we can assuming we have a function, we can replace these output variables with function notation. F of x. This is f of x, y. Okay, and so the idea of the x-intercept here in 2D, the idea of the x-intercept, well, we know that if we're thinking about just y and x, then you're setting y equal to 0 and solving for x. So the x-intercepts are going to be the solution to the equation, to this equation, when you set f of x equal to 0 and then solve for x. That's like setting y equal to 0 and solving for x, because the function is unique because it's got this lone output variable on one side and x all over here. So you're just setting, it's like you're just setting y equal to 0. You just set f of x equal to 0 and solve. And if you're thinking about, okay, where does the function intercept the f of x axis or the y axis? Well, all you're doing there, if you think about it, is you're just setting x equal to 0. So and solving for y, well, that's just evaluating f at the function at 0, right? Because it's like if you have y is equal to 3x plus 2, setting x equal to 0 and solving for y, it just means set this expression equal to 0. It's already solved for y. You don't need to solve for y. So you just set the function, evaluate the function at 0. That's the y-intercept. And then the x-intercept, again, you just set the expression equal to 0 because the y is by itself. Okay, and if we extend this, let's come to a function of two variables. Well, if we're trying to find where the graph intercepts the output axis, the z-axis, well, you just need to evaluate f of 0, 0. Set x and y equal to 0, and that's it. You don't need to solve for this. You just, because it's already solved for the function. Now, if you're thinking about how do you find like the x-intercept or the y-intercept? Well, this is a little bit different because you can't just say set f of x, y equal to 0, because in that case, you're finding where the graph intercepts the xy plane. So you need to say, if you're trying to find where the x intercepts, you need to say this, f of x 0, and then set that equal to 0. So if you had, it's like if you had z is equal to x squared plus y squared, or f of x y is equal to x squared plus y squared. Well, to find the x-intercepts, you need to set z equal to 0 and y equal to 0. Well, okay, that's exactly what this means. You're setting y equal to 0, leaving x untouched, and you're also setting z equal to 0. And then you just need to solve that equation. So now we can see in general, if we abstractly extend a Cartesian coordinate system to like 5 variables, let's say you have f of x, y, z, w, p. So this would be in 6 variables if you include the output variable. Well, okay, where the graph intercepts the output axis is here, and then where the graph intercepts any one of these axes, like the z-axis, you solve this equation. Okay. So now here's an example. If we've got the function f of x is equal to x squared minus 4, what are the x and y intercepts? Well, the y-intercept, the output axis intercept, is easy. You just evaluate the function at 0. So when at minus 4 on this axis, at minus 4, that's what's going to intercept. Okay, now to find where it intercepts the horizontal axis, you solve this equation. So you solve x squared minus 4 is equal to 0. So that's a difference of 2 squares. So at x is equal to minus 2 and at x is equal to positive 2, that's where this is going to intercept. It's going to intercept the x-axis. Okay. Now, what about the domain and range of a function? Well, this is just like the intercepts in the sense that there's no difference between how we find the domain and range of just any relation compared to how we would find it for a function. So we already understand what it means to find the domain and range of a relation, but a function is just a type of relation, right? So the domain and range of any relation is just, so a relation is, it's some set of points with, with two or more variables, the set of points, which is like these lists of ordered pairs or ordered triplets, etc. The domain is all of the possible inputs, the set of all of the inputs that you could input and you're going to get an output. That's the domain. The range is the set of all of the possible outputs you can get. So if we look here they give some graphs of functions. We can look at this from the domain and range from a graphical perspective, or if we're dealing with an equation, we can look at it from the perspective of actually the equation itself, or maybe the list of points. If we're here, this is not an equation, this is a list of points. So we can look at this graphically, think about the domain and range graphically, or from looking at the equation or the list of points themselves. But so here, what would the domain be? What are all of the possible inputs that you can input and you're going to get an output? But you don't include duplicates. So in that case, the domain here would be the set, and you do so. You can input -3, -1, -3, -1, and then 0, and then 2 and 4. Okay, now the range is all of the possible outputs. You can get -4, 1, 3. You can also get 4, but we're not going to put 4 twice. Okay. Now here, these are like equations. So you've got these, it's an infinite number of points. So we write the domains and ranges here in interval notation. So the domain here would be, so you can't input -3. There's an open circle here. So -3 has no output, but it's anything from -3, not including -3, to positive infinity. You can input and you're going to get an output. All right. The range is you can't input -2, or no, you cannot not input. You're never going to get a -2. No matter what you input, no matter what, from any number from -3 to infinity, you're never going to get -2 ever. But you will get, you can always get, you'll find a way to get something that's greater than -2. Anything greater than -2. All right. Now here, the domain, it's kind of hard to see, but you can input any number you want, because this has these arrows here. So if you follow this far enough, it would keep extending. It extends all the way to the left and to the right. So any input you want, you can input, but you're not going to get an output that's greater than 4. You can get an output that's equal to 4, but you'll never get an output that's greater than 4. So that's the range. Now, just note though, it's easy to over time start to think that the idea of domain and range only applies to functions. No, you could do this with any relation. So we could come back here. So, okay, this isn't a function, right? This is a relation. Well, what's its domain? It goes, it's 0 to, you can input anything from 0 to infinity. What's its range? You can get anything from -infinity to infinity, because these arrows are going to go forever. Okay, what about this circle here? That's not a function. Well, the domain is you can do so, input anything from -1 to 4, including -1 and 4. What's the range? Well, you can get anything from -4 to 2, including the endpoints. See? So domain and range applies for any relation. And even as we did earlier, it's not even just equations, any list of ordered pairs. You can have a list of 5 points, and that's it. And you could think about what's the domain, what's the range. Okay, now, you can have, there can be restrictions on the domain of a relation. And in particular, we're thinking about relations in the form of an equation, but I mean, I guess you could think about restrictions on even just a list of points as well, potentially. I mean, you can do whatever you want. You kind of decide this based on the circumstances. But so here they give an example of so here's a function, but you could do the same process with a relation if you wanted to. You have the function x squared plus 2, but it's stated that, okay, but there's a restriction. This is just for x is greater than or equal to 0. But like, okay, you could do this with, you could have the equation of a circle. That's not a function. And you could put that same restriction if you wanted to. You could also put a manual restriction on the range if you wanted to. So in that case, if we're trying to answer the question, what's the domain of this function here, as well as what's the range, we have to consider this restriction. So typically this would, with no restriction, x squared plus 2, you could input anything into a polynomial. Well, now it's just x is greater than or equal to 0. But then you also have to think about, okay, well, does that change the range as well? The fact that you can't input anything that's less than 0, sometimes it will, sometimes it won't. Now, there can also be restrictions on the domain, and this doesn't really come into play for the range, but there can, like, you can manually restrict the range if you wanted to. You could say y has to be less than 2 in this case or something, if that applies. But when it comes to domain restrictions, there can be restrictions in the sense of if you have a function like x plus 2 over x minus 3, then there's a natural domain restriction here because you can't divide by 0. There's no way you can't, you're not going to be able to input 3, x is equal to 3 here and get an output. But this doesn't really, something like this doesn't really come into play for ranges because the range just is what it is unless you manually apply a restriction. Okay, and so when it comes to these natural restrictions on the domain, what do we need to be looking for? Well, up to this point, there hasn't been many situations that result in something that you can't input into like an expression. It's only been dividing by 0. You can't divide by 0 in all circumstances. And then the other situation was a negative number under an even root radical, which once we learn complex analysis, we're actually going to be, that's not going to be invalid. We'll be able to do that. But even after you learn complex analysis, there might be certain situations where you say, no, you're not allowing for imaginary solutions and whatnot. So you'll apply the restriction. Okay, you can't have a negative under an even root radical, and that would be a part of the natural domain restriction. However, just note, dividing by 0, there are no exceptions. You can, in the year 2025, at this point, you cannot divide by 0 under any circumstance. Okay, so if we look here at you have, let's start with this function here. What's the domain of this function? Well, there's no manual restrictions that were applied externally. Okay, so we can kind of start by assuming, well, you can input anything. Okay, but then we look at this and see that it does involve division. There's no radicals, but it does involve division. So we have to say that, okay, this denominator here cannot be equal to 0. Now, sometimes it might be the case that there is no possible x that makes the denominator 0, so you're fine. But in this case, we can solve this and see that, no, there is a case. X can't be equal to 5/2. Now, the range, we have to look at the graph, and we need to understand how to analyze expressions a little bit more, which we'll do a lot of that in calculus. But the range is just going to be, you'd have to, what are all the possible outputs? We'd look at the graph and see what all the possible outputs are. But it's when it comes to evaluating domains, it's a lot easier in the sense of just looking at the equation. You can see what you're allowed to input, right? It's harder to look at an equation and figure out what exactly are the outputs that you're going to get, because you have to kind of evaluate the equation. But as far as the domain, you can look and see, what can I input into this? And in general, with expressions, you can input whatever you want unless it involves a even root radical or division. So, okay, what about g of x is equal to, what about this function? Well, there's no radicals, okay, but there is a division, so x squared plus 4 can't be equal to 0. Other than that, you can input whatever you want. Well, okay, this is nice because this can never be equal to 0. There's no solution to x squared plus 4 is equal to 0. So, okay, you can input whatever you want here. The domain for the first case, x plus 3 over 2x minus 5, is just x can't be equal to 5 halves. The domain for the second case is x can be any real number. Okay, now let's see. This third case, this is an even root radical. If it was odd root, there would be no problem for any situation. Well, here, assuming we're not allowing for complex solutions, then 2 minus t needs to be greater than or equal to 0. It could be equal to 0, that's fine, but it just can't be less than 0. So we need to solve this inequality. So we get t is less than or equal to 2. There we go. That's the acceptable inputs. That's the domain. T is less than or equal to 2. Okay, now last we've got m of a is equal to the absolute value of 4 plus a. Well, okay, there's no restrictions on an absolute value. You can input whatever you want to an absolute value. So a can be anything. A is any real number. Up to this point, the only restrictions we have to think about are even root radicals and dividing by 0. And then for the rest of this entire course, the only other restriction is going to come up with you can't have something less than or equal to 0 inside of a logarithm, unless you're allowing for imaginary type complex numbers to come into play. Okay. Now, interpret a function graphically. In example 10, we will review the key concepts studied in this section by identifying characteristics of a function based on a graph. So yeah, this is looking at a function graphically and interpreting different, the function evaluated at different points, etc. Can be useful for developing your intuition of functions. So if we've got the graph of this function, what is f of 2? So that's at x is equal to 2, what is the function equal to? It's going to be one value, or it wouldn't be a function. Well, okay, it's 5. F of 2 is 5. Okay, what about f of minus 5? Okay, at x is equal to minus 5, what's the graph at minus 5? It's going to be this one point in the graph at minus 5. Well, it's an open circle here. It's undefined. Undefined at minus 5. No output. Okay, find all x for which f of x is equal to 0. Okay, well, in this case, we're allowed to have separate inputs corresponding to the same output. So there can be multiple x-intercepts for a function. So, okay, so we can keep that in mind, that we're looking for the x-intercepts because we've set the function equal to 0. We've set the output equal to 0, so we're on the x-axis. Well, we can see, okay, so we've got minus 4, x is equal to minus 4, and x is equal to 4. Those are the x values where the function equals 0, the x-intercepts. And there can be multiple of those. But now, what are all the x values for which, okay, well, no, they don't ask us about the y-intercepts. There can only be one. Think about how there can only be one y-intercept for a function, right? Or it wouldn't be a function. Okay, but they don't ask us, or they do ask us about that. So, well, yeah, these are going to coincide. That's the definition of the x-intercept of a function, is you solve f of x is equal to 0. And then the y, there has to be just one y-intercept, and that's going to be at 0, 3. Okay, now what are, for all x for which f of x is equal to 3, well, okay, this could be multiple x's. You could have this different x values that correspond to the same output, but let's see. Well, yeah, there are, right? There's f of x is equal to 3 for an infinite number of x values, anything from minus 3 to 1, including the endpoints. Then the function equals 3, but that's fine. You have separate x values that correspond to the same output. So this is anything from minus 3 to 1. Okay, the domain of the function is, you can input anything from minus 3 to infinity, not including minus 3. And then the range is anything from negative infinity up to positive 5.